And back again. That sounds happy, doesn't it? All right. Yes, so what actually are neutrinos? Well, it's kind of like saying, what actually are electrons? I mean, you know, so let's get philosophical, you know, let's get like, well, you can never know the thing in itself and all this kind of stuff, right? But they're a type of subatomic particle. It has no electric charge. It has very little mass. It only interacts with other types of matter via what we call the weak nuclear force, which means that they're very hard to detect because the weak nuclear force is called the weak nuclear force for a reason. It's not a very strong way for matter to interact with other types of matter. So really, you know, it comes down to it's a subatomic particle that has very little mass that only interacts via the weak nuclear force. That's what it is. It's about all I can say as far as that's concerned. So they're kind of ghost-like particles in a sense because they don't interact very strongly. Yes.
How can we prove the conditions in the sun's core from observing neutrinos?
Because remember, photons take a couple 100,000 years to get from the core to the surface because they're bouncing around so much. Because neutrinos interact so weakly with other forms of matter, they free stream right out of the core as soon as they're created. And so, as a result, neutrinos allow us to see what's happening in the sun's core essentially now, as opposed to photons, which take a long time to get out of the sun's core. And so, that's essentially what it comes down to. Is seeing neutrinos allows us to know what's happening in the sun's core today. Now we kind of, okay, we see the kinds of neutrinos we expect, and so that's kind of the story as far as that is concerned. But we also use neutrino detectors to observe neutrinos from other astrophysical sources now, and so we hope to learn things from that as well. Yes?
Can you just explain the general relativity in terms of curvature of space-time around objects having mass? Is that like the time thing? Or is that something
It's part of it. So space-time is every point in space and every moment of time all put together. So it's a sort of unification of the concepts of space and time. And so according to general relativity, gravity isn't actually a force. Gravity is a curvature of space-time. The reason why gravity affects the motion of particles is not by putting a force on them, it's by having them move through curved space-time, which affects the way that they move as a result of that. So gravity both changes the shape of space and it affects time, the rate at which clocks tick. They're both built into the idea of curved space-time. Curvature of space-time both involves changing the shape of space and changing the rates of clocks. And that's kind of, oh great, that's what I'm talking about. That's kind of as much as, you know, I can readily say here without going into all the like detailed math.
So why does gravity change the way of space? Or why does it?
Well, it's what gravity is. So, in other words, you're asking a really fundamental question, which is kind of like saying, why is force mass times acceleration? In other words, we may be able to come up with a more fundamental theory, like string theory, that can explain gravity in more fundamental terms. But on some level, the answer to your question is that we can figure out what the laws of physics are, but saying why are the laws of physics the way they are, is a metaphysical question. We can say that gravity is curvature of space-time. Why? Because nature thought that was a good idea. And that's kind of the way it is. you know, I can't give you anything more fundamental, it's just the way the universe works.
So I don't know if I want to ask, but
No,
like,
go ahead.
no, like, so like this whole like concept is just like really like hard to like wrap your mind around.
Which is not
So-
surprising, physicists think it's hard to wrap their minds around too.
Yeah. So
Yes.
like for like the test, are you gonna like ask like in-depth questions about it, or just like general like?
What I'll have you do is I'll give you the Einstein equation, and then you can solve it and show, for example, the distortion metric. I'm going to ask generic kinds of questions.
Okay.
Right.
Okay. That's like
And you're going there, huh?
I'm just gonna take an L on this part.
Right, yeah. Yeah, it's just a punt. You're right, yes.
I've got a little one.
Yeah.
Why is helium fusion called a triple alpha?
Because it uses 3 helium nuclei, 2 carbon nucleus, and another name for a helium 4 nucleus is alpha particle.
Okay.
So 3 alpha particles become a carbon shell, triple alpha.
Thank you.
You're welcome. See you tomorrow. It seems like we reached that magic moment. Right? There's always that threshold that gets crossed. This time was pretty successful. Sometimes it's like people like in the car where you're daring them to veer off course before you go over the cliff, right? Everybody's like, who's gonna get up first? Who's gonna? This time it's like, no, we're out of here. So okay.
It's gonna be 50 questions again?
Yep. 51, where number 51 is, for 2 points extra credit, write down the full set of reactions with proton-proton.
Yeah, sure.
Yep. Okay. Okay. Damage to the earth. Sure. But it's not. And if you actually, if you took a chunk of neutron star material, I didn't mention this, but suppose you tried to just grab a chunk of neutron star material. Once you got away from the neutron star's small gravity, it would actually just vaporize. I don't think it would stay in neutron star material. I think it would be magic if it came together. It do this thing of falling through the earth. I wouldn't worry about it. Because again, I don't think the neutron star material would stay neutronium if you took it out of the neutron star. So this is the least of your worries, let's put it that way. No, but on the other hand, it's a perfectly good, comic book weapon. You could certainly turn it into a nice comic book weapon because you can do anything in comic book. So.
What about like anti-gravity stuff?
Well, that's a whole other topic, I guess you could say.